Good day, everyone. Welcome to ME158. So this is the recorded lecture that was supposed to happen Friday afternoon. I hope you're all safe and prepared if ever um, Typhoon Mani or Pepito should strike your general vicinity. Now, this will be a little short, but this is probably the first lecture where we do have some semblance of dynamics calculations. I'll make it simple just so that it's easier to digest. It's more important for you to get the concepts before the calculation rigors. So before all this, we actually got through anatomical motion, anatomical joints, muscle and muscle models. For this topic, we'll be covering what we call inverse dynamics, the anatomical simplifications that we conduct, like the segment mass, the centers of mass, and the radius of gyration, and the reaction forces and moments generated by those positions, those velocities, those accelerations, and the actual muscle force. The last one will be just a very brief overview. So first and foremost, the name is kind of weird because it says inverse dynamics. Now in NSI 12, I'm not sure if it changed now, but during engineering dynamics, there is usually no distinction of subtypes. Like there are in this case, for this kind of classification, there are two, inverse and forward dynamics. Now, from NSI 12, we usually learn just dynamics. This concept, the modifier, the modifying word, is from the concept of moving machines. Now, if you have a robot arm, normally you wouldn't really know the no, not scratch that. When you have a robot arm, usually when you want your robot to go from standing vertical, like the hand is facing up, and you want to order it to move down and pick up something, what you do is command motors to exert a certain amount of torque to get the robot arm where it needs to be at a certain point in time without crushing or overshooting the object that it has to pick up, I mean. So that would be forward dynamics. Your input serves as your input, the forces, they are known to you, and you have to solve for the position, velocity, and acceleration those forces and torque develop. Now, for the body, this is not the case. It's not easy. We don't have a control unit which gives a preview of how much torque or how much force each muscle is generating. Although we do have ways to indirectly measure that, but it's actually easier to monitor the position of body segments with respect to time. So that's easier. It's also easier to just do some body segment characteristics. Well, when I say easy, it's quote unquote easy. There's a lot of things that went through this. And third, it's also easier to just measure the external reactions exerted on the body in comparison to just measuring the internal force. So that's why it's called inverse dynamics. Like you're trying to figure out backwards based on the position, velocity, and acceleration of different links of the machine, what force or torque is needed to generate that kind of position characteristic. So you're taking angular positions, velocities, accelerations. You're taking the mass of links, the mass inertia of links. You're taking the reaction forces that are applied on the links, and then you're gonna generate reaction forces and reaction torque. Now to keep things simple, we'll just be dealing with links or body parts that don't move. So we're just going to limit ourselves to just thetas and x's. So and to be a little to add more simplicity, we'll just be examining the a 2D simplification of our forearm. So that includes the hand, the um the more distal part of your arm, and for some cases in in the following examples, we'll also include the humeral part of your arm. And also we'll be making assumptions na things will be evaluated as if they are just flexing and extending. So, even though you can do other motions with your arm, we'll evaluate our arm as if it can only flex or extend. So, nakita niyo na yung mangyayari. Basically, we're going to simplify body segments into links, but there's actually plenty to decide on, such as where does each segment start and end exactly, and yeah, where does it start? Where does it begin? It should be where does it end? Yeah, sorry for that. So to assist in this endeavor, this is why I said it. Measuring body characteristics is quote unquote easy. Um, it's hard to examine body size. Like for example, if you wanna measure the mass moment of your hand or the center of mass of your hand, like how are you gonna do that? If it's still attached to your body, so there are two areas that researchers in the 50s, the 60s, and the 70s, even up to the 90s, they used to validate some characterizations of body segments. So they use anthropometric measurements of living people. So that's the first. And the second is they use cadavers which they can cut up and study. So in 1967, there was this group of them studying Goshran. I'm not sure if that's how you pronounce it, their name. So, their team actually defined the beginning and ending of each body segment according to the center of the joint. So, when you move your body or when you move your elbow, um, there is an instantaneous center of rotation at every position of your elbow, like with respect to your forearm and humerus. They're just trying to find the average location of the center of rotation of your elbow. So I'm not sure how deep the process was for them. They do have an extensive paper. The reference is I'll show the citation and the reference, but it seemed like a very long tedious time for them. They actually had to hang a piece of hand from a string to find the center of mass of that of said hand. So yeah, it's pretty gruesome, but there are no pictures. They're just illustrations of things being cut up. So yeah. Now this is all well and good because as engineers, we'd actually prefer it if the links are defined from the joint centers that connect them. I think that is more accurate to the movement of the body. However, it is much more taxing to find on a living specimen. So 2 years later, there are people who actually try to do a little bit of making things easier. So instead of trying to locate the actual joint center, they define the body segments to start and end based on some bony features that researchers and even the clients can feel themselves. So instead of cutting up your own body and then putting it back together to find the center of rotation, you can just feel for certain bone processes under your skin, and then you can define that, okay, this is where approximately my forearm starts, and then this is where my forearm ends. So this is what Clauser, McConneville, and Young actually did. So, for example, in our upper extremity or our arm, there are three major major bony processes that define the three segments of our body. So for the elbow, from the humerus, I didn't add the definition for the shoulder anymore, but I added in the elbow. So for the elbow, the process to track is called the radial. So, as you can see in the picture, it's a bony process that you can feel in the dimple of your elbow if you cast your arm straight. You can try to do that. It's somewhere there. If you can feel a bony process, that is where the humerus ends and then the forearm starts. Now for the ending segment or the ending position of your forearm, it's called the stylion. So for the stylion, try to keep your hand in a neutral position. If you feel a bony protrusion just before you reach the wrist, that might be your stylion. So the radial and the stylion are defined as the two endpoints of your forearm. Now for your hand, they do have measurements for that. They assume that your hand is actually only your palm. So it's kind of strange. Basically, Clauser's team, they ended the hand approximation up to the middle knuckle, basically. So your hand is just up to the knuckles. It's not part of your fingers. It's kind of weird, pero yeah, that's part of the anatomical simplification process. So yeah, they also defined other body segment parameters such as percent body mass of each segment and percent of the segment length. So this is the full table. It's really impressive if you think about it, like how they extensively did this kind of research. If you want to count how many cadavers they used for the 1969 study, I believe it's more than 10. I'll have to check. There are more studies later than this. There are studies that are more recent. However, the other study that my reference brought up mentioned that they used around six cadavers for the much later study, which might ano although it's much more recent, because this 1969 study did studies on more than 10 cadavers. The research essentially becomes more at least there's some more backing to it. At least there's more meat to the data. So yeah, if you notice in this table, we have segments and endpoints defined, and there's also an order to the endpoints. So if you recall, the proximal direction is towards the core of the body. The distal is towards the extremities. So you have three columns here. You have segmental mass. So that is the mass of each body segment. We have a center of mass, and we have a radius of gyration. So the radius of gyration, if you can recall, it is imagine a body that is spinning around an axis. So if the body spins around that axis, it has an inertia, a mass inertia around that axis. Now, if you want to simplify the entire body into a point mass, the distance of that point mass from the axis will be the radius of gyration. So radius of gyration, it is actually an indirect way of getting the mass inertia of a segment without calling it mass inertia. Yeah. I don't know what they were thinking in 1969, but yeah, that was this is a thing. So yeah, the thing about the data points of these three columns is that number one, they are normalized. So for example, the segmental mass is divided by the total mass. So what you're actually getting in this column, the column here, are all mass percentages. Now for the remaining two columns, if you observe, there are two columns, sub-columns each. There are there's a proximal column and there's a distal column. So the proximal column is measured from the most proximal endpoint of your body segment. So like for example, if it's the forearm, if you select the R proximal subcolumn, the measurements there, which are divided by the segment length, they are percent segment length from the most proximal part. So if it's the forearm, it's from the radiale, or let's just say let's just call it the elbow. So yeah, it's percent segment length from the elbow. Now for the radius of gyration, there is no distal measurement. This is just, from the center of gravity of your segment, and then there's a proximal measurement. So those are the properties, or those are the mass properties that were measured per body segment. And this is just a simplification. I just reduced the number of columns that we'll be looking at so that it's less confusing. So here we have the segment mass, center of mass, and gyradius of each segment. So the segment mass is percent body mass. It is in percent body mass, and the rest, they are percent segment length from the most proximal part of the segment. So let's do some exercise. Uh yeah. There's also a disclaimer. But na nakita ko. When we see the radius of gyration, so radius of gyration is also gyradius. We are assuming that it is only for the flexion and extension of the body segment. When the body segment does anything else, if you can kind of imagine, the body segment has a different profile um depending on how you're using it. In flexion and extension, perhaps you can just simplify it into a certain shape. But when you're abducting and adducting, a that same body segment, its inertia characteristics could change. And if you try to anatomically rotate some of those body segments, their radius of gyration does indeed become much more different. So the gyradius values here are presented assuming that they are only being used in flexure and extension. So abduction, adduction, and anatomical rotation, those will generate different values of radius of gyration. So now, let's look at a practice run. So this is Dave Bautista now. He's lost quite a lot of pounds, and his current mass, at least I think this was last year or early this year. His current estimated mass is around 108 kilograms. Now the task here is to estimate the probable arm mass of Dave Bautista. Now, to do that is actually rather simple because thanks to the study of Clauser et al., we do have the body segment mass percentages of each body part. So, since we also have the full weight of Dave Bautista, we could estimate the weight of his entire arm. So, to do that, we take his full body mass, then we add up all the segment mass percentages that are relevant to us, which frankly is all of this. So 108 kilograms, and then we add these all up. So they result in a certain percentage, and it gives us the weight of one of his arms. And that is 5.2812 kilograms. Kinda heavy, still. Do you think you can do an estimate for the mass of your arms as well? So here's the thing also. The parameters of each segment here are done on averages. They are, as you've recalled in the previous modules of ME 158, the averages, they're not quite good. They're not as good as um, in covering the entire human species when you're designing ergonomic features for work and for comfort. But for us, it at least simplifies the calculations much better. So more or less, his arms could be 5.3 kilograms, or it could be more, it could be less. When you are building muscles in your arm, muscles tend to be of higher density than fat. So, his your arms compared to Dave Bautista might be lighter or much more depending on how much you work out or if how much you eat essentially. So for the next part of this segment, we're going to estimate the locations of the center of mass of each segment while they are mapped on a 2D Cartesian system. So this kind of task is a purview or a simplification of what the live tracking system does when it's watching you move in the motion capture studio. So it doesn't have the luxury of it doesn't have the luxuries that we have. No, we can just, oh, this is the arm, let's just measure it from this angle, from let's just measure it from here to here. Let's just measure it from here to here. Computers have some trouble doing that. Like most live tracking, they do it in a global coordinate system, and then going from the global coordinate system, they try to localize to do what we do. So yeah, it's a lot harder for us, but this is a purview of the workspace that live tracking works in. So okay, we have endpoints. We have the proximal endpoint for our humerus, we have the elbow, we have the wrist, and then we have the endpoint of our hand. And they each have coordinates. Now, this is quite simple for us because we've learned the task of measuring distances between points. So if you can recall, hold on. If you can recall. So to measure, oh, hold on. To measure the distance between points, what you do is to take the square root of the sum of the squares of the difference between the coordinates of each endpoint. So this is the basic measurement of distance between points. Make sure that you do not forget this. This could show up at any point in your engineering career. So this is good for measuring the length of each segment. Now, why are we getting the length of the segment? That is because our center of mass definition is based on percent segment length from the proximal side. So let's say, for example, let's try to get the length of the humerus from here to here. So from the humerus is actually quite simple. This is, hold on. So if you complete this calculation, this should be around 430 millimeters. So this should be around 430 millimeters if you do the calculations right. Now, to locate the center of mass of the upper arm, we know that the center of mass is located 51.3% of the way. From where? From the most proximal side. So for the upper arm, it's here, the most proximal side. So we approximately locate 51.3% from the shoulder to here. So if you do that, the coordinates that you will get, okay, so how will I now model the coordinates? So let's start. So this x1 and y1. In order to get to this point though, what we need is essentially a kind of difference between these 2 points. So x2 minus x1 plus y2 minus y1. So this is x, this is y, um, along the length. So this is kind of irrelevant right now because if you simplify this, you'll just simply get x2 and y2. But if you're getting the center of mass, like here, you can just write in the percentage. So this the percent COM, this the percent COM. So if you multiply that, you should get the following values. So this thing is 34.5 and negative 217.9. So yes, that's around, I think that's the right value for the center of mass of the upper arm. For the rest, I leave it as an exercise. These are the correct values. Hold on, let me erase. Yep. So these are the correct values. 34.5, negative 217.9. For the forearm, it's approximately here, it's horizontal, weirdly. Horizontal. And then for the hand, it's just a little close to the wrist, but it's here. All right. Now let's go to the other practice. So that was the center of mass. What about the mass inertia of our body segments? So to get the mass inertia of our body segments, oh, since we have radius of gyration, we can just take the mass. We can just take the mass and then we can take the radius of gyration. So to do that, we have to get the mass first. This is the part that we skip because when we got the full arm mass of Dave Batista, we got the full arm mass, but we didn't get the mass for each of these segments. So what you have to do is to multiply the appropriate mass percentage for each segment. And that is, to do that, you get 2.84, 1.74, and 0.70, around that. So this is the mass. These are the masses of the segments. Now to access the radius of gyration, to access this, you need to compute for the length. So here you have to use the this is between points formula. So you have to use this in order to get the lengths. So the lengths here are 430. This is 380. And this is around 90. Approximately. Now, the gyradius or the radius of gyrations, they are presented as percent of the segment length. So you have your segment lengths, you just have to multiply the appropriate percentages. 59, 49. And then once you obtain the radius of gyration, square these values, then multiply them with the masses. And you should get the mass inertia on deflection and extension of each body segment. So the answers actually are these. All right. So you can try to practice it at home. If there seems to be something wrong with the calculations, you can just ping me or message me. But yeah, those are the calculations. Now, we are trying to locate for the center of mass and calculate for the mass inertia in order to do the next step, which is the balancing of forces. So for now, we will not examine systems that are moving or experiencing any kind of reaction, external reaction force. For now, like for this example, the forearm is just being held uh, almost horizontally, not quite horizontally level, but horizontal. So we're going to use the center of mass, the mass inertia for this task. I actually scratch that. The mass inertia is not used for this. So because the forearm and the hand, they're just being kept level mostly. There is only one external force acting on them, and that is gravity. So here, for example, at the most distal segment, you have your hand. It is being acted upon by gravity, but in order to maintain the position that it is right now, your body has to generate some forces in your muscles, in your ligaments, and that can be simplified as reaction forces and reaction moments about the ending segment of your hand. So you have horizontal, vertical reaction forces, and you also have that moment. Now, these reactions, they transfer over to the next body segment that is more proximal. So that is your forearm. It sees the opposite of the reactions that the hand experiences. However, not just that, the forearm also experiences the gravitational force, and of course, it's just staying still, so there is no acceleration and velocity. In order to resist the gravity on the hand and on itself, um, there has to be another set of reaction forces and reaction moment that will resist the increasing effect of gravitational force. So this is the force balance or the free body diagram for the hand and the forearm. When you put in the humerus as well, you can imagine that there is much more strain. The forces that are being resisted increase as you go towards the proximal side of your body, which is kind of consistent also with beams. So your hand is a beam. Interesting. And since we are only keeping things static, our force balances, they are all at zero, static equilibrium. Now for practice, we have a human arm that's being kept still. So let's calculate the internal reactions at the wrist and at the elbow. So this one will be an assignment, and I think this is just a simple assignment because we've already done the prerequisite calculations. Now you just have to solve for the necessary forces. So things are not really that complicated when nothing's moving. However, when things start to move, things get crazy because if you note from the static if you note from the static analysis or the static body, um, we didn't really apply the position. No, actually, the position is kind of relevant, but for other parts of the body, it is more relevant. However, we didn't look at the velocities or accelerations because there was nothing in the system that was generating that. Now, when you have a moving body or a moving organism, things get a lot more complicated because although you see here you have dynamic equilibrium for translational coordinates, you have mass times acceleration. For bending moments, you have mass inertia times the angular acceleration. You also need the angular velocities in order to fully grasp the complete um complete positional picture of the moving organism with respect to a snapshot in time. So this is where J, the mass inertia, becomes more relevant. This is where omega and alpha become more relevant, and um, unfortunately, we will not be covering it for this part of the this part of the lecture. So yeah, this is full inverse dynamics now. And note that this is still in 2D. When we go to 3D, it will be a lot more stingy, a lot more complicated. So now, okay, how do we do this? How do we measure position, velocity, and acceleration of the body? How do we measure the reaction forces that the body is experiencing? So this has been actually covered before in one of your previous modules in IE. Now, in order to do a complete inverse dynamics analysis, you need basically two things. So you need live tracking of body segments, like not just plain live tracking, but um, a very high quality, high resolution, and high sampling rate live tracking. So you can track the position, velocities, and accelerations of each part of your body. Before, they used to put in motion trackers on athletes. Sometimes they're made to wear mocap suits as well. There are technologies now. I believe they're using neural networks in order to track the body accurately without having to put motion trackers on. So that will be actually a game changer for inverse dynamics. So that's the first part. And the second part is you need something that can measure reaction forces. If it's just walking, force plates underneath the platform can help with that. If it's for sports, I think you have to have another accelerometer at the relevant position. Like for example, when you're evaluating baseball hits, you might want an accelerometer somewhere there other than the force plate, but perhaps you're only concerned with the position of the body, so it might not be actually used. So the setup, at least from the bird's eye view, would kind of look like this. You need multiple cameras because when the body is moving, some of the trackers can be obscured. So at most, no, at least two cameras should be able to see each motion tracker in order for the data to be good fidelity. And of course, if it's just walking, you can put force plates underneath the walking path to record the pressure or the forces that are being exerted as somebody is walking. So the end result of inverse dynamics would be calculations of bending moments at respective joints in your body. So, like for example, this is a record of reaction moments when a senior is walking and that senior is enabled by a support. I didn't quite catch what kind of support it is, but you can see in the top left graph that support is generating a reaction moment in order to facilitate the walking cycle. This, by the way, this graph is a single walking cycle, and some you can see some partitioning of the walking cycle. So RHC is right heel close. LTO is left to open, I believe. So yeah, those are abbreviations for parts of the walking cycle. Now this is all well and good, but this kind of modeling again, it assumes that our bodies work the same way as machines. So it kind of assumes that we have motors installed at our joints. which is not the case. We do have quote unquote motors, but they're spread along the lengths of our body segment. So in actuality, the reaction forces and the reaction moments, they are the sum of the individual reactions of each muscle, each ligament, and even bones during the motion. So this is the actual for this image. It is 2D, so it is not capturing all of the muscles that are being stretched or compressed during this instant. But yes, this is a good illustration of how complex the human body is. Yeah, it is that complex. So yeah, that is it for this purview into inverse dynamics, and here are the references. Hopefully, we'll be able to meet by Wednesday, and then we'll be able to do some activities on Friday. So thank you so much, and see you around.